Morning, everyone. It's great to be here. Thank you, Eduardo, and the Colloquium committee for the invitation. I had a blast yesterday. It was excellent meeting with several of the faculty members and the students. I wish I could spend more days to learn about what you guys are doing, but amazing, amazing. So more than what they learned from me, I think I learned a lot from the faculty and from the students. It's really great to be here. Today I'm going to talk about Oak Ridge National Lab's AI initiative. This is a lab-wide cross-cut effort that looks at how AI is sort of transforming various types of science and national security applications, and how to empower these AI applications. So this is not just about AI for X, Y, and Z, but this is about developing secure, trustworthy, and energy efficient AI for various types of science and national security applications. What this talk is not about is, we are not going to focus entirely on large language models. If you are expecting that, I want to lower your expectations, and I also want to bring this message that AI for science and AI for national security is much, much more broader than just language models. Language models are important, getting a lot of attention, but the number of interesting and challenging problems that we have in science and national security are plenty, and we need a much more comprehensive effort and approach to solve these type of problems, which are very, very important for the nation. As I mentioned, AI is already transforming science and national security. It is used to accelerate scientific discovery, to fortify energy infrastructure, and to enhance national security. These are few exemplars from one national lab, right? So from Oak Ridge National Lab. So we are using, so in this case, like Spallation Neutron Source, it's a large experimental facility where we use neutron source to look into the internals of materials, right? So think of this as X-rays, looking at your, passing through your bone, and you can look at the X-ray and see what is inside, right? So similar to that, we can use neutron source to analyze materials. Why we need to do that? Because by analyzing the structure of the materials, we can understand what is internal to that, and how the property of the material changes for different conditions, and so on and so forth. The amount of data that is generated by these types of experimental facility are huge. It's not possible, sort of business as usual, like scientists taking experimental data, going back 6 months, analyze the data, come back, and do the next set of experiments. Right? So these are shared experimental facility, and our ability to analyze the data then and there is transformative. By doing so, we can quickly recalibrate the facility or to reprioritize what type of experiments that we can do. And that means the time for insights and time for discovery is moving from 6 months to a matter of days. And that is really, really transformative. And AI is playing a major role in doing so. In the manufacturing demonstration facility, we use AI and robots to come up with optimized way to do manufacturing and to demonstrate that this is possible. In the Center of Structural Molecular Biology, we use AI and microscopes to analyze plant phenotypes to really understand how the plants can act, grow, and resilient, can be made more resilient under various types of climatic conditions. The Oak Ridge Leadership Computing Facility, traditionally, is large supercomputers. So this is a facility which hosts the fastest exascale, fastest supercomputer, which can perform exa operations per second. And this is the only exascale machine for open science. There are other things in the closed space and industry, but this is the only machine in the open science. And why we need that sort of machine? Think about climate simulations, think about nuclear fusion simulations and fission simulations and so on and so forth. These are computationally expensive simulations that can take several months on even the fastest supercomputer, right? Great, so we can build faster supercomputer, we can move from 1 year to 6 months, but still that's a problem because 6 months is still a lot of time on these big machines. Think about the energy, think about the power, think about the effort that goes into it. One way that we are really accelerating the science or the scientific simulations there is to develop surrogate models. So looking at the simulation and see where the simulation spends most of the time. And often these are partial differential equation solvers. So can we build surrogate models for those PDE solvers to go from initial conditions to the solution rather than solving this iteratively? Right, so solving that iteratively takes several hours per iteration. By doing surrogate models, we can get solutions in a fraction of a second. That means we can run climate simulations instead of 6 months. We're talking about doing climate simulations in a day. And that is transformative. Now, in that case, we can run larger number of simulations. We can ask a lot of what if questions on these simulations. What happens if these parameters, if this type of carbon emission strategies are implemented, how the climate will change, and so on and so forth, right? So there are various kind of things that we can do on top of that fast simulation. Oak Ridge is known for cyber research, cyber science and research facility, where we are experimenting with various types of cyber methods to secure infrastructure. And now we are using AI to increase the efficiency of these methods. And high flux isotope reactor is the one in which where we develop isotopes. And isotopes, as you know, are dangerous, right? So often these are run by robots, and these robots are often manually controlled, which means that there's a lot of time that goes into operating these robots, and also analyze what type of isotopes that we get. No problem? Okay. So again, here we are using AI to really accelerate how we can manufacture these isotopes. These isotopes are used for medical purposes, for space applications, and so on and so forth. Great. So what are the challenges associated with these AI developments? Is it like done deal, or we are just scratching the surface? The answer is we are really scratching the surface of what AI can potentially do. And it is also challenged by the fact that AI has several paradoxes, right? By the way, this is an image generated by ChatGPT by giving, generate an image that talks about paradox of AI. So what are really the challenges, in particular in the context of AI for science and security? AI applications, when it comes for development, often it is easy to demonstrate, right? So you can write code in Jupyter Notebook and then say, oh, this works. But it's very, very hard in production to productize that, to take that code and to take that model and put that into an experimental facility and make sure that the model works. We have seen that already with various types of autonomous car controllers, right? Everything works great in a simulation or in a control setting, but then you put it on the road, things can go bad, right? So that's how we are seeing accidents. And think about a multi-million-dollar experimental facility. And we want to put an AI to control that experimental facility. We have to be absolutely sure that this model works. Right? We cannot even take a 5% risk. Think about AI models controlling a nuclear reactor. Right? We have to really operate at the edge, at the outliers. What are all the potential risks of model going bad? The model going bad, there's another camp that says model going bad and it's going to kill us all. That's not the thing that we are talking about. We are talking about model going bad and what are the consequences of those bad decisions, bad predictions, and so on. So that matters a lot. I mean, there's one thing about having a bad product recommendation in Amazon, a bad movie recommendation in Netflix. But when it comes for a bad drug recommendation, and if we go and manufacture the drug and put in in the body? What are the potential consequences? So it's a high consequence application, right? So how can we make sure that we take into account the risks associated with bad AI predictions? Hard problems are easy and easy problems are hard. For example, we are at the point of the civilization where we can take all the data that is available to us, all the knowledge that is available to us in the form of text, and synthesize that knowledge in one single model, a ChatGPT type system. But we don't have a robot that can tie a shoelace in a very consistent way, right? So that's so easy for us, but it's very, very hard for AI systems. And this is true. We have to understand what type of AI systems that we are building and what are all the limitations, rather than saying, oh, AI is going to solve one model that can rule all, right? So we need customizations, we need to understand the limitations, and we have to really think about what are the design principles that goes into those AI models. There is also ever-growing open problems, right? 1 year back, we were not even talking about alignment problems, right? So there were some conversations about alignment, but now alignment is a major problem. More complex, more sophisticated, and more powerful AI systems that we built, the kind of open research problems is growing rather than decreasing, right? So this is something to think about, because we don't understand how these systems operate, and that has consequences, right? So if we know exactly why this system operates in this way, then we can have a good handle on that, but it's not the case. So the number of open research problems associated with complex and advanced AI systems are increasing. Humans still remain a roadblock in the sense that, for alignment, to make sure the system works properly and so on and so forth, we need an AI expert to do this, right? How can we scale this out as we build more and more AI systems and put that into production? How can we make sure that these systems work with humans, but in a scalable way? There are unique challenges associated with cyber physical systems. Again, there's one thing that the system is inside the computer and we are interacting with it. The thing about systems doing cyber physical control, that opens up so many problems related to safety, security, and trustworthiness. What happens if there is a decision that drives the cyber physical system into some bad regions in the space, and what happens? What are the consequences? So there are a number of grand challenges in AI for science and security. So there is this Nature paper that talks about how AI is going to transform the science. There is no second thought about how AI is going to transform science. We can write it in a stone now, and we can declare that it's going to transform science. There is no second thought about it. But what is important is how we are going to tame it, how we are going to make it work in various types of settings in a reliable way. That is the simple statement about the challenge that we face with advanced AI systems. And it is not surprising that the government came up with this executive order that talks about, okay, we have to build AI systems, but it's not about building the most advanced AI systems or Gemini or ChatGPT, right? Or it's not about, oh, we need to regulate how these things. But what the executive order is about, how to build safe, secure, and trustworthy AI systems, and how to use it in a proper way for various types of applications. The overall AI initiative is focused on developing secure, trustworthy, and energy efficient AI. There are many different topics within these high level trusts, but we looked at what does it mean for science, and it's not because of the executive order that we did it. We have been doing this for a while, and it really boils down to the applications that we have within Oak Ridge, within the Department of Energy complex. So the initiative itself has two axes. The first one is AI for scientific discovery and complex systems, AI for experimental facilities, and AI for national security. And the second axis is a foundation axis. The foundation axis focuses on secure, trustworthy, and energy efficiency. And these are all not mutually exclusive. For example, within the secure, we have cybersecurity and robustness. And within the trustworthiness, we have validation and verification. If you take a large model and want to do validation and verification, it can be quite computationally expensive. How can we do that in an efficient way? That matters. Similarly, uncertainty quantifications for AI models are the first-class citizen, right? So without uncertainty, we cannot say whether the model predictions can be trusted or not. So how can we build those type of models with robustness guarantees or with alignment and so on? So it's a sort of a combination. It's often informed by what type of applications that we are after. So the AI for scientific discovery and complex systems, it's the application axis. We are focusing on material design and material discovery. Material design, these two are the sort of major topics across DOE and across almost all major labs. So it's essentially, how can we design new material? How can we design materials that sort of satisfy various types of constraints and various types of objectives that we are after? So material form the basic building block of everything that we do, right? Starting from what we touch and we drive, we compute, materials have profound impact on our lives. So how can we make material discovery faster? And we have two different thrusts within that. So the first one is, okay, how this is traditionally done. So we want to analyze the material structure. So material structure is material molecular structure. And we want to understand the properties of that. The traditional way to do that is to do molecular dynamic simulation, which is often expensive. Like even to study one structure on big machines, you have to spend 1 hour. Now we are talking about billions and trillions of different structures, because it's all about finding a needle in a haystack, right? So that's the kind of problem that we are after. And traditionally, it's driven by very computationally expensive simulation. Now, what we are trying to do is to develop surrogate models for those simulations. So given the training data of molecular structure and certain properties, we can generate those training data from simulations or already existing data, then take that and develop a surrogate model that goes from molecular structure to certain properties, right? So that's the surrogate aspect. So once we have surrogate for molecular dynamic simulation, then we can go and do design. So now the design cycle is much more easier or much more less expensive. So this surrogate model can predict the property of a particular molecular structure in a matter of milliseconds. If that's the case, then we can use those surrogate models to do design. So now you say what type of properties that we are interested in, then we can put an optimization loop on top of this surrogate model, and then loop it through to find better molecular structure. And we have done that for a number of applications, and we have successes with the zeolite and high entropy alloys. So these are all generated by surrogates and an optimization loop on top of surrogate. On the experimental facility side, so we are developing surrogate models, the AI ML surrogate models, to create digital twins. So for example, take power grid or nuclear reactor are some of the experimental facilities that we have, including the leadership computing facility. The first and foremost thing that we want to do is, whatever type of experiments that we have to do on these type of facilities are expensive, right? So we cannot ask what if questions directly on a nuclear reactor and say, okay, what happens if I do these type of controls on this nuclear reactor? First of all, it's dangerous, and second thing, it's expensive, right? So doing any type of real experiments on these type of facilities are expensive. So, but we do have data, and that data can be used to create digital twins, fast digital twins. And once we have those digital twins, then we can use that. So digital twins are AI ML models, and use those digital twins to do optimization on these experimental facilities. And also we can do real-time control. So for example, in the spallation neutron source, we are using a digital twin of a particular experimental facility, a particular experimental instrument, and use that digital twin to do real-time control. So real-time control is updating the status of that particular instrument at the time t and retraining the model. So think of this as a continual learning model, and then use that model to do what needs to be done for the next time step, t+1, and then do this control. Right? So creating a digital twin is key, and this can be done in many ways. And in this case, digital twins allow us to do optimization, control, and to ask what-if questions and analyze sensitivity of different parameters. So we are developing this assurance stack, which has uncertainty quantification, validation verification, explainability and interpretability, and more importantly, privacy. So privacy is becoming a key topic, not just for healthcare applications, which is obvious why we need privacy there, but also experimental facilities where we can use privacy preservation techniques to enable data sharing across different modality of those experiments or different experimentalists using their data. So by having this privacy preservation, now we can look at data from different scientists who are not ready to share the data because it's very sensitive until they go and publish that data. But by doing this privacy preservation, we can learn from that data and provide models that can be used by all other scientists, right? So AI for national security, we are combining AI for security research and security for AI research, right? So this is about building building methods, developing methods to secure AI models, and how to use AI models for cybersecurity, right? So it goes both ways. And we are looking into safeguarding AI data and models from unauthorized access, monitoring mechanisms and auditing mechanisms for AI operations and frameworks, and understanding how one can poison data and model. This is super important for science because these models are built on scientific data. And if someone can go and poison the data, then the whole model can be misguided. And there are ways to do that in a very, very targeted way. And we don't want to take chance on that front. We cannot lose our guard saying that, oh, these are scientific data, and we are fine with people accessing it in a very, very naive way. Yes, we have to provide access, but at the same time, we have to develop methods to address data poisoning, model poisoning, and detecting and finally coming up with mitigation strategies that allow us to secure these models. Validation and verification is becoming central to many AI applications that we have. We can develop AI models, but how to ensure that this AI model, the data-driven machine learning model, is validated and verified for certain properties. One way that we are looking at this problem is because we are building different types of models, large models, and how to validate and verify these models for fairness, privacy, adversarial robustness, and so on and so forth. We are developing sampling-based methods because these are general purpose and can be scaled relatively easily compared to more formal verification methods. So the idea here is we have a model, we have an input space, and let's say we want to verify a logical property, and that property, we can sort of say, what is the threshold associated with that property? For example, we have a model and it has, okay, I want to have a robustness of this model according to some metric and say 5%, right? I can allow 5% in terms of robustness. I can sacrifice 5% in terms of robustness, and how can we verify that? Or if we say 1%, then how can I verify? So the way to do that is we have this large-scale sampling mechanism that goes and pokes the model at different areas. Right? And by doing so, we can identify regions where the model is working really well, and we can collect statistics and we can provide guarantees on that. And we can also poke the models in the regions where the model can make mistakes, right? But just by adding a noise, it is making a different, it is giving us completely different results. So those are the sort of boundaries where the model sort of doing various types of classifications and so on and so forth. So we poke the model more in those space and learn where the model is making those mistakes, and then increase the sampling intensity in those regions to come up with guarantees. As I say, you sample 1,000 times, out of this 1,000 times, 10 times, this model is going to make a mistake. That sort of guarantee. And we can extend that to other metrics such as fairness defined by particular application, because fairness is a very broad term. We have to come up with certain metric, but once we come up with that metric for the particular application, then we can go and do this large scale sampling and poke the model at various boundaries and build this probabilistic guarantees. Okay, so this is sort of a high level overview of what we are doing at Oak Ridge on this within the AI initiative on secure, safe, trustworthy AI. Now I want to sort of take a little bit deep dive on trustworthy AI for science at scale. Essentially, we are combining large scale computing, advanced optimization algorithms for designing AI models in an automated way, but also building these models with trustworthy capabilities. In other words, uncertainty quantification capabilities. Again, this is an image from ChatGPT. So this is a very large supercomputer and advanced AI sitting inside, scientists are around, and these are the science applications. So this is the overarching theme. Okay, when it comes for designing neural networks, so how we usually design these models, either we download something that is already in the GitHub or we start from scratch. In either case, the number of design choices or the degrees of freedom in neural network design is a lot, right? So even for this simple graph neural network, if you want to make this network powerful, we have to deal with various types of choices. And exactly for this simple network, we are looking at 10 to the power of 10 possible designs. It's like number of Lego blocks, and we have to find the right combination to put together so that this model works well. So working well is not just about accuracy. Okay, hold on. It's about various other metrics. And often it's a manual process, trial and error, and time consuming, right? If you think about it, the irony is we say AI is going to transform the world, AI is going to automate X, Y, and Z, but at the same time, the very fact that the AI that we design is not automatic, it's manual, right? So it's an iterative process. How can we streamline that? How can we automate that? So one way to think about it is what are the degrees of freedom? So there's sort of algorithm hyperparameters where you define the neural network and then say, okay, what are the hyperparameters that determine how we train the network? And that goes from different types of optimizers to use, learning rate, mini batch size, learning rate scheduler, adaptive batch size, and so on and so forth, right? And then you have architecture hyperparameters that says how this network will look like, right? So is it, what is the structure of the neural network? That is determined by number of layers, fully connected, convolution type layers, for the graph applications, you have different types of graph aggregation, and so on and so forth, right? And also there is residual connection, skip connection, that often helps in many of the neural network design. One thing to note about the skip connections is skip connections look like this. So in a typical neural network, you go from one layer to another layer, you connect them, and so on and so forth. With the skip connections, you can make connections between layers that are not immediately next to each other, right? Why this is important? Because if you make those type of connections, this is how this optimization loss surface looks like. So this is without skip connections, same network. If you try to optimize, the optimizer needs to navigate this loss surface. And it's a very rugged surface, right? As soon as you add skip connections, the loss surface becomes really, really smooth. And that is important because this smooth surface has a lot of desirable mathematical properties in terms of robustness, in terms of adversarial attacks, in terms of generality or ability to interpolate and extrapolate and so on and so forth. So this type of loss surface is very, very desirable. So the challenge is how to do this type of skip connections. Again, if you go and look at how the skip connections are already made, it's fairly regular, right? So, but then no one can stop us from doing a skip connection from here to here or from here to here. So there are various ways that one can do skip connection, and that increases the degrees of freedom. How can we automate this process? Algorithm hyperparameters, architecture hyperparameters, and this type of skip connections, right? So we are talking about, even for a relatively simple network, really large design space. How can we automate this design process? One way to look at this problem is from a mathematical optimization perspective. Right? So the formulation is shown here, and it is a bi-level mathematical optimization problem, and on the lower level, you have the usual training problem, right? Which is you have the algorithm hyperparameters, you have the architecture hyperparameters, you fix the network, you fix the hyperparameters, and then say, okay, I want to go and do the minimization on the training loss, right? So this is what we do day in, day out, right? If you're working with AML models, you want to train this model with respect to some objective function, and that is often the training loss. That's a lower level problem, training problem, which is defined on the training data. The way to automate that is to define another layer of the problem, which is the upper level problem, which says, okay, I'm going to make the algorithm hyperparameters and the architecture hyperparameters as a part of the search space. And for a particular combination of the algorithm hyperparameters and the architecture hyperparameters, I'm going to solve the lower level problem, which is the training problem. So essentially, for various combinations of algorithm and architecture hyperparameters, we had to go and do the lower level training problem. So pick a particular configuration on the hyperparameters, and then go and solve the lower level problem. And then based on the result that we get, go and find a new set of configuration and go and solve the lower level problem and iterate this. This is the bi-level optimization problem that we have. Okay, so the upper level problem is often defined on the validation accuracy. So we often have this validation data and can be defined. This upper level problem should not be done on the training data, but it should be done on a different set of data. So we developed Bayesian optimization approach to solve that bi-level optimization problem. A quick primer on Bayesian optimization. So let's say you have one-dimensional input, which is the input hyperparameters, and the output is your validation accuracy. Bayesian optimization is all about fitting multiple models on a limited set of training data, right? So limited set of data. And here, let's say we have this hyperparameter configuration, we have the validation accuracy. Another hyperparameter configuration, validation accuracy. Let's say 4 or 5, right? And then Bayesian methods basically fit multiple models on those data. Why? Because note that here we are talking about a problem with limited data, right? That's why Bayesian optimization is desirable. And let's say these are the configurations that we already evaluated, the one shown in the black. And if you fill multiple functions throughout that points, essentially your uncertainty, because all the functions will pass through this point, your uncertainty will become 0 for the areas where you have evaluated. And the more farther you are from that particular point, your uncertainty increases, right? Is that clear? That's the crux of Bayesian optimization. Once we have this, right, so uncertainty associated with any type of input, then we can use that to drive the optimization. So saying that, okay, I'm confident in this region, I don't want to sample more. I can go and sample in a region where I have high uncertainty. On the other hand, so, this area, I have found really good solutions. I want to sample more, right? So for example, this is a good region, right? So I want to sample more here to find configurations that are better than what I have found previously. And this is how it looks like. So it's an iterative algorithm, and you start with some initial configurations and you see this uncertainty. Again, it's on one dimension, how this cartoon. And what you see here is how this uncertainty changes as you sample more and more. Essentially, you want to trade off exploration with exploitation. You cannot keep on going and sampling from region where you have found good solution, because that can result in poor local solution. On the other hand, you don't want to always go and sample from regions where you have high uncertainty, because you can have regions with high uncertainty, but those are bad regions. In those cases, you just need 1 or 2 samples. You don't want to go and sample more hyperparameter configurations from those regions to identify the best configuration. It's waste of effort. So we have to trade off these two. The point is, Bayesian optimization is designed for very computationally expensive simulations, in the sense that each evaluation is very expensive. In our case, it is expensive, right? So training a neural network for each hyperparameter configuration is an expensive process. But we can scale this approach and use large supercomputers such as Frontier and Aurora to really reduce the time for that iterative process. The traditional Bayesian optimization algorithms do not have this assumption that you have a large compute for doing this. And they are often designed for one at a time, which means that take a hyperparameter configuration, evaluate, take the results back, put this back and retrain, and then go next iteration. So it's a step-by-step process, right? So it's a one at a time. If you have 1,000 GPUs at your hand, you don't want to do that, right? So you want to accelerate that. At a given point of time, you want to have thousands of neural network hyperparameter configurations that are being evaluated, and some of them will finish, and you take those results, iterate, fill them up, right? So essentially, this will allow us to reduce the time to do this whole process. So this is the approach that we have developed to scale Bayesian optimization. Often Bayesian optimization and Gaussian process are interrelated, in the sense that Gaussian process is the method of choice when it comes for Bayesian optimization, but Gaussian process has scaling problems. You cannot take large number of configuration results and put that back into Gaussian process, retrain, and generate configurations at a faster rate. So we develop methods based on ensemble of regression trees. So imagine these multiple functions. Each of the function is a decision tree, and we can use an ensemble of such trees to come up with uncertainty. So think of each of these curve is a decision tree. Okay, so that's the first thing. And the second thing is this hyperparameter space is mixed integer space, which means that it has integer parameters, categorical parameters, and real parameters. How do we... Good. So how to deal with that, right? So Gaussian process often work on continuous parameters, right? Whereas regression trees are really good at handling this side of mixed integer parameters. So that's another reason why we went for regression trees. And then we have a few other mechanisms to improve the scalability of sampling. And this is the reason, so how we scale this approach is shown in this cartoon. So let's say you have this one-dimensional problem with uncertainties like this. And if you say, okay, I want to go and sample configurations. I have 10 GPUs, right? Or 100 GPUs at your disposal. How can I sample? So I give this uncertainty, and I give this this model how to sample intelligently, right? So if I ignore that fact that I have 100 GPUs, then I will sample one here. Then based on the result, I will update that model and then go and sample the next configuration, right? What happens if you just say, okay, here is the largest area of uncertainty, and I have 100 GPUs. I want to sample 100 configurations. What will happen is all your 100 configurations will be from this one particular region. You don't want that, right? All we need is one configuration from here. And that will give a lot of information about this region. So essentially, without looking at what the results of this particular sample, we need to move to the next one. And the approach to do that is called constant liar. So you basically tell the model its prediction is right. What will happen? this uncertainty will go 0, right? So here the uncertainty will go to 0. And then you will move to the next most uncertain region. Then sample a configuration from there, send it to the GPU, and tell the model its prediction is right. What will happen consequently? This uncertainty will become 0. And the model will move to the next region, and so on and so forth. So in this way, without looking at what the results are for a particular sample, a particular neural network that we are training, we can go and sample intelligently in the space based on various types of uncertainty. So this is about scaling this method even further. So if you're talking about hundreds of GPUs, a single manager that sort of samples this configuration and sending this to GPU and get the validation accuracy back, and then iterate this process. Right? So that can work well for hundreds to thousands, up to thousands of GPUs. But if you want to go more than that, then the communication will become a bottleneck. Right? So for that purpose, we have designed this decentralized mechanism, which not have any manager at all, right? So each worker will have its own search, and it will do one-at-a-time evaluation. But at the same time, when it needs to refit the model, it will get the results asynchronously from all other workers. Right? So it's a all-to-all communication. We had to do a bit of optimization for this all-to-all communication, but eventually that sort of a decentralized search approach scales much, much better than the single manager, multiple worker type methods. So here are some results on science application. So this is about sea surface temperature forecast. Here we want to develop a neural network model for forecasting sea surface temperature. And here is the thing about scaling this approach and doing this dramatically, right? Manually designed neural network has an R squared of 0.96, and that's the baseline that we have. And we have on the x-axis you have time, right? So this is a wall clock time, and each curve represents the number of nodes or the number of GPUs that this search approach took. And with the smallest 133 nodes, you have this one where you say, okay, within an hour we could generate more than 10 models that are better than what a human can do. If you scale this approach up to 512 GPUs, then you can see within an hour, we can generate more than 1,500 models that are better than model designed by a human. Right? And then you can do this for like within 3 hours, we can get with the 512 GPUs, more than 3,000 models that are better than what a human could potentially do. Right? It's a push of a button. And here are some science results. Essentially, this is often run with simulation, like computational expensive simulation. And HiCom is a model that took 800 core hours per day, and CSM is 17 million core hours to do the forecast. And once trained, this model can do forecast within a millisecond. Right? So there's a training cost, but once trained, this can do really, really faster forecast compared to traditional simulation. And this is how the results look like in ANOVA. This is the ground truth, HiCom, CSM, and the pod LSTM, which is this LSTM model that was designed automatically by Bayesian optimization. What we can do with those ensembles, right? So there's one thing about generating a lot of models for ensembles, but we also use those ensembles for uncertainty quantification. There are two forms of uncertainty, which is a data uncertainty and model uncertainty. And these uncertainties play a major role when it comes for trustworthy model prediction. So the ariatric or the data uncertainty is uncertainty associated with the data. It cannot be reduced by collecting more data. On the other hand, epistemic uncertainty is uncertainty where you don't have data. So if you know what your epistemic uncertainty associated with the model, you can go and sample more from that region and reduce that uncertainty. More importantly, uncertainties with the predictions, we can build trust around the predictions from the models. So this is a typical deep ensemble approach, which is like one model with different initializations, and then we can build an ensemble But the problem is there is no variation with respect to the hypothesis. So if you think about each hypothesis is represented by a neural network model, the underlying hypothesis remains the same, and that's a typical approach. But given that we have the capability to generate large number of ensembles, diverse set of ensembles, we can do much, much better than these type of traditional deep ensemble approach. Here is a little bit of theory. I will skip in the interest of time, but essentially it's about estimating the data uncertainty and model uncertainty from ensembles of neural networks. This is how it works in practice. We run the neural architecture search, hyperparameter search, and get a model catalog and do a model selection on those catalog. And from that catalog, we can then go and estimate epistemic and aleatoric uncertainty. Here is how it looks like in practice. When you get this uncertainty from the data, we can see epistemic uncertainty is almost zero. Darker means it is zero. It means that we have a very good set of models, very high predictive uncertainty, with very high predictive capability. On the other hand, aleatoric uncertainty is higher and it's often correlated to the sensor locations. And that we found like very interesting because without telling the aleatoric uncertainty or what type of noise associated with the sensors, we could estimate those uncertainties. And the errors are often associated with these uncertainties as well. So we did the same for the disruption prediction in fusion reactors, build ensembles and using architecture search. And one thing to note here is this is how the search looks like, x-axis time, y-axis validation accuracy. This is the baseline model that was published in Nature paper. And when we did this automated approach, we could outperform the model that was published in the Nature paper within 30 minutes. It's not just one model that we have hundreds of models that are better than what was published in the Nature paper. And here is a baseline, and models that we found are faster to train and they have higher accuracy as well. And then we can use those uncertainties coming from the ensembles to detect the fusion plasma instability well in advance. So for example, this is a manually tagged thing which says, okay, fusion plasma is stable, 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 and then the human tagger said it become unstable here by looking at the data. If you have uncertainty associated with the prediction, then you can see this is happening much more well in advance, and using this metric, we can say this instability is coming and use that. So we are using these type of approaches to optimize models for various types of metrics. So accuracy is one thing, but depending on the application, we have fairness, privacy, transparency, and so on and so forth. And this is again another result from the search, which basically says, okay, this is 3 objectives, and this is the best model, like large model. So the box size means size of the model. This is the best model one could potentially get. But at the same time, if we can sacrifice a little bit of accuracy, then we can get really, really smaller models, right? Smaller boxes. That is, the batch inference time is much, much smaller, and the number of parameters is also smaller. Right? So we are talking about 2 orders of magnitude faster models than what is best out there. And this ability to navigate the search space and generate thousands of models allows us to look at these kinds of trade-offs. A big thanks to my collaborators. It's not a single-man job. A lot of people contributed to various types of research that I presented today, and I would like to take this opportunity to thank them. And at a high level, this is what we are doing within the initiative, and acknowledgements to the sponsors. Open for questions, and thank you for the opportunity.
Oh, I have a question.
Yes.
Yeah. Thank you for your presentation. I think it's more informative. So actually, my research is related to the robustness. So I'm wondering if any existing project in your group is related to this area, related to robustness.
Yeah, so the validation and verification that I mentioned, so that's the one thing that we are really building as a capability and verifying robustness for climate models. So we are doing this surrogate models for climate simulation, and we really want to understand what are the robustness associated with the models, because by adding this aleatoric or the data noise, your predictions can go back. So there's one thing about looking at how we can tease out that data noise, but also we want to understand how the noise in the data affects the predictions. So or how the model, how much the model actually changes with respect to noise in the data. So there's a climate model. There is also healthcare applications where we are looking at analyzing the cancer reports, and their robustness is a major concern. We want to build more robust models because at the inference time, we don't have control about what type of data that we are going to see. So the only way that, that is one thing about having a validation data, but really what we have to do is to analyze the robustness of the model with respect to various types of noises, noise distributions, and so on and so forth, so that we can build confidence around these models and do model selection. So again, if we have 100 models and if we can do robustness testing on each of this model, then we can select the top 5, 10 diverse models and use that for uncertainty. So there are various ways that we are looking to incorporate robustness testing and robustness measure for model evaluation. So I can add more. So these are some of the key applications that we are looking at: climate, healthcare, and I also talked about the digital twin for the power grid. So that's another application that we are looking at.
Okay, thank you so much.
Yes. So just kind of follow up on that. You said that the digital twins were using AI. Can you elaborate or give an example of how AI factors? Because that's a little counterintuitive for me. Like, do you use AI to build the digital twin?
Yeah.
So you basically have inputs, outputs, and you're having it learn some sort of model. So you're
correct.
You're not
with incorporating the physics. So that's where the physics-informed neural networks come in. Often, we know a lot about the physics, the bounds, and what type of operating region that it should operate, and so on and so forth. So we use all those as a part of the model definition, physics laws, and so on and so forth. So that allows us to incorporate more domain-specific knowledge into that. And digital, so the 2 digital twin projects that we are, there's more, but the 2 things that are within the initiative are the one for the power grid, and another one is for the spallation neutron source. So these 2 things, yes, input, output, time series, take from the actual machine and actual infrastructure, and build a model that says, okay, given k time steps based on the state, we want to see how this system will behave for the k plus m time steps. K time steps with specific input, how this will change k plus m time steps.
And it's just too complex to construct by hand, a model by hand, because you have all the parameters, everything about the physical system.
Yeah.
So
no, so these are not analytical models. These are still machine learning models because yes, we know the inputs and outputs, but we don't understand or we don't have all the information to model the complexity of the systems, right? So power grid, it's highly interconnected, and the way that dynamics evolve, yes, we can do some analytical calculations, but often they are off, right? So one way is to use that analytical equation and then learn the error and then correct the error with the AML models. So that's another way to make these models more impactful, powerful.
So those are better than just a model that's been deployed like on an RTDS or Opal RT, like a real-time simulator. Like when you get a digital twin, you're getting a more accurate model over a larger section of grid or something.
Absolutely.
Okay.
So one thing that existing simulation sort of lacks, also in weather, is ability to incorporate real-time data, right? So I can build a digital twin and do something, but ability to incorporate how the state changes and how the system evolves over time. and use that information. Because if you try to do a data assimilation on a big simulation model, it's expensive. If you want to build this type of calibration on a large simulation, that is also expensive. But with AI models, you can do this in fraction of a second. And so that is the transformative capability. So have this computationally cheap model that can ingest the real-time data and evolve and reflect what is the current state of the system, and use that to do forecasting for the next gate time steps. That improves the forecasting accuracy by a large margin.
Yes. So just following up with that, would that be supervised learning? Because you have your inputs and you're using the outputs as a form of supervised learning then?
Correct.
Okay.
It's a supervised learning with continual learning, depending on what type of assimilation that we do or what type of corrections we do. There is a bit of continual learning that needs to be done. Continual learning also opens up other set of challenges. In continual learning, we often have this catastrophic forgetting, which is like if you keep on taking the new data and retrain the model, you'll completely forget what it has learned in the past. So we have to take that into account, like learning the representations from the past, or using some sort of replay techniques. So essentially it's saying that you replay what it has seen in the past. It's pretty rudimentary, right? Like you think about it. So those are the things that we have to incorporate. And doing this at the edge or in a near real time, that is a big challenge, right? So doing this, the power constraints with the energy constraints, or doing this in a real time setting, operating under a minute, how can I take the data and put that in the model, retrain the model, and then provide more accurate forecast? So that's why I said there are a lot of challenges associated with it, and they're just starting on the front.
Thank you.
Other questions?
There's one on chat.
Well, it just came up. Yep. I'll read it. It says, how are the time energy takes to train the IA surrogate models taken into account in relation to how much cost they will save in replacing the direct simulation?
Oh, that's another great question. A lot. So think about these computationally expensive simulations that we have for sea surface temperature, right? Here. Okay, so I was talking about this. HiCom is a simulation code, and that need to run for 800 core hours a day, right? And CSM is 17 million core hours on the Yellowstone machine. So those are the forecasts, HiCom and CSM. If you look at the forecast from that, because the very fact that they don't have the real-time data assimilation, you can see those results are not that great. Even for that result, they had to run for quite long time, and it's very, very significant in terms of the computation time is very, very significant. Whereas this model, right, the data-driven model, we trained it in 3 hours using 500 nodes, right? But then this has the ability to take the real-time data and do the forecast. So it always looks at the K previous time steps and use that information to do forecast for the K plus M time steps. And if you're talking about energy cost, right? So inference can be done on your laptop. So training, yes, we had to do that. But then once it is trained, inference is on your laptop. Or we can even, these models can be made even smaller and can be put in a much more energy efficient devices. We are talking about, first and foremost, reduction in simulation time by 1000x, right? Computation time, reduction 1000 times, the 1000x means it's 1000x savings. And also the energy associated with, energy costs associated with running these large machines. Again, this provides advantages in those cases. In this particular application alone, we are looking at 1000x speed up, 1000x savings in computation time, 1000x savings in energy cost, right? So that's the thing, barring the initial training time that we have to do for the machine learning model development.
That's not even taking into consideration the human resources that you would have to spend on those other.
Absolutely, yes. We are totally talking about the computation and the energy costs. So that's one of the major themes for Department of Energy labs, like how to build surrogates for these computationally expensive simulations and speed up those simulations, save time, energy, and cost, and do this at either in real time or near real time, right? So doing this type of data simulations in real time for climate or for power grid, that is transformative, really transformative. So you don't have to move, and it also provides a lot of other benefits, like you don't have to move the data back to the compute center, right? So the data movement bottleneck is the real bottleneck, right? So as soon as we have to move the data, then we are facing so many challenges, both in terms of privacy, but also in terms of data movement cost. Having these models operating at the edge, now we can address several problems related to that. Okay.
Maybe Prasanna, since there are the student here,
Yes.
you want maybe to talk maybe about the
Internships, yeah. So that's another pitch I wanted to make. So yes, Oak Ridge has several internship programs, and we are really looking forward to host students from the university. And you will be working on really cutting edge AI, ML problems related to science and national security. So we have, what I showed is only, the tip of the iceberg. Really, we are scratching the surface. There's so many problems across the lab. Problems in the sense not like problem, but problems to solve. Okay, and really, these are problems that need solutions, and these solutions are really cutting edge, and for several problems we haven't even found solutions. So you will be working on really problems that are highly relevant for the nation, and making progress in those fields. So please do consider applying for the internship programs. Happy to provide more info. I will share the website with Eduardo. But if you have questions about those internship programs, please reach out to me. I'm happy to help.
What is the schedule on applications and when you hire?
Now, so this is for summer. So we have student programs across the year, but now we have opened up the application. This is the time for the application, although we think it's a little late because we had to fight with the industry. But I think this is the time, and there are several programs that are open, and I highly recommend students to look at those programs. And I can also connect you with the internship coordinator at Oak Ridge, and they will be able to give more information about the programs as well. So this is not, and again, the AI is not just compute, the computing division centric. AI is happening across the lab. So I'm pretty sure you will be able to find projects that interest you.
There is a question online that says, what kind of academic backgrounds do you look for in potential interns? It's a broad range. We go from undergrad all the way up to grad students. And for students who are finishing up the graduate studies, Ph.D., there are several openings in the space. So please also look at the jobs webpage of Oak Ridge. And if you have questions, please reach out to me. I will also connect you with the HR for trying to fill those positions. So broad range, undergrad, all the way from undergraduate to PhD.
Question? No? Then thank you so much.